So we had a longish chat yesterday. So we'll just continue from what we were talking about yesterday. So hopefully today we can sort of gloss over the nitty-gritties, but please feel free to ask again if anything is unclear or if you want me to repeat something, right? Okay. So this is where we started yesterday, where we said that collider is sort of an independent measure uh, of trying to look for dark matter because you don't depend on any astrophysical uncertainties or anything like that. So you might basically have a sort of clean channel to look for these particles. We also made the caveat that if you produce something at the LHC, then we know that it is stable only at the time scales of the LHC detector. So it may not be the actual cosmological dark matter, but it would be a hint of something new and invisible. And then we can ask whether it's the right one. Okay, so this is the agenda for today. So I'm going to give you an overview of what kind of LHC searches exist. So yesterday we talked about some very simple ones, but maybe we can go to some more complicated ones today. I'll also talk a little bit more about how these searches compare with direct detection searches and ask the question that somehow didn't get asked yesterday. I thought it would. Is that given that there are so many parameters and you can basically play the game of just changing parameters and your results go away, is there value in these searches at all, doing these searches at all at the LHC? And then I will talk about some non-standard dark matter searches, which are not really dark matter searches as such, but searches that correspond to some well-motivated dark matter models, okay? Then we can have a quick talk about some gaps that are currently in the search program and what can be done about them. And then there is just a summary of whatever the limits we have. So this is something that I tried to convey yesterday, that there are multiple ways of describing a dark matter model. On one end, you have an effective field theory picture, which may be very, very simple. The advantage of this is that you just have the one operator that will give you all kinds of phenomenology. So direct detection, indirect detection, collider production, everything is through one diagram. The con is that unfortunately, since effective field theory necessarily requires that the momentum transfer that in the UV completion is very, very small, it fails at the LHC because LHC is a high energy machine, so it doesn't work. So we looked at this in detail yesterday. On the other hand, you have these super complicated complete models, which may have hundreds of parameters and hundreds of new particles. So supersymmetry is an example of this. The advantage of these is that it's theoretically very well motivated. All the couplings and what they should be is very well known. However, it's you require to assume far too many things to make any progress, and basically you will pigeonhole your results in certain slices of parameter space or phase space. Okay, so there's these two extremes. Both of these things are done. What LHC normally does nowadays is it sort of tries to stay in the middle and uses something called simplified models. So the idea there is that you look at these complete models for inspiration, and then you just focus on one production mode at a time, and then look at all the decays possible within that production mode. So we took an example yesterday where we had this singlet triplet model, and we found that there could be some 8 production modes that from just one production process, right? Because there are many gauge bosons in it. So, so that's the idea of simplified models, where you avoid the bad high energy behavior of effective field theory, but you still don't have as many parameters as a complete model. So that's what most LHC searches do now. And then again, to recap, we have the standard freeze out picture, which informed the very first LHC searches, where the idea is that you have some simple process, annihilation process, that goes out of equilibrium and sets the dark matter density. And if this is the process, then you sort of reverse this diagram to get the LHC search. Okay, so we talked about this yesterday as well. And we said that we want to basically look at something invisible. You cannot look at something invisible unless there is something visible to say that it is invisible. So you have this sort of something extra, some initial state radiation or something like this that will give you a handle on your LHC searches. So that was the very, yeah. Yeah.
Oh, it's the initial state.
Yeah. No, yeah, okay. So let's make it a little bit more concrete. So again, we talked about these searches yesterday, but the idea is suppose you have a diagram like this, then you can reverse it and have this diagram. But you could also, for example, have a mediator that is charged under standard model, right? So that means you could also reverse that diagram and just produce the mediator in pairs and then look at the decay of those mediators. Okay. Often what happens is also you can, so if you have a coupling like this between dark matter mediator and standard model, you could also produce mediator singly and then have decay of that mediator. So these two kinds of things where you just have the T channel production or you have a single mediator production give you this monojet kind of signature, which we looked at yesterday. If you pair produce the mediators, then you have basically pairs of things happening. So you have multiple standard model particles plus missing energy. So this was the example yesterday where we took two W's or W and Z plus standard model, right? So so basically these are missing energy searches, both of them. So you have something else happening plus missing energy, okay? So this was the standard. And this was very, very well studied in multiple search channels. And the advantage of these simple models is that you can have signatures in multiple search strategies, okay? So you can look for the same model. So if you complete your operator with a Z prime, it usually gives a signature in direct detection. It will give signature in indirect detection because it will still cause annihilations in galactic center and so on. And you can also reverse it and produce it in colliders. So you have signatures in all three. That is true for all of these. For SUSY, the answer is always it depends, because there are so many particles and so many parameters that you can produce it in certain parts of the phase space and not in certain ones. Okay, so this was the picture. Unfortunately, what happens here, as we all know, is that there is no detection in direct detection or indirect detection or at colliders, right? So, so this was just in what I showed yesterday. I don't know what is wrong with this plot. It didn't show yesterday either. All right. So this is the status from the LHC searches. So the reason I have this is yesterday we had some discussion about the comparison of axial vector and vector mediators. So remember, this model is where you complete with a Z prime, right? So you have this quark to dark matter and an initial state gluon like this. Or you can have basically just quark to quark via the same Z prime. And we saw yesterday that this direct search for Z prime using this diquark channel gives you a much stronger limit than direct searches for missing ET, which is the small triangle here. Okay. So the takeaway from this is that if you directly look for the mediator, you get far better bounds than if you look for missing energy. So as you can see, this was in some slice of choice of parameters. And you can try to, using this model, you can try to overlay it with the direct detection searches and see how that compares. Okay. So here I'm going to compare both the vector mediator and axial vector mediator. So these are essentially the same. So this ET plus miss is the same thing as here, right? And then you have these vertical lines which correspond to the dilepton and dijet searches and so on. Okay. So you see that for this particular case where you have spin independent scattering because you have a vector mediator, you see that LHC search limits are somewhere here, whereas the direct detection search limits are much stronger. So the LHC doesn't compare as well, but the situation reverses if you go to spin dependent scattering. Because direct detection searches are sort of less sensitive to these, right? They don't have as strong limits. So you can see that best direct detection limits are only of the order of 10 to the minus 39 for spin dependent, whereas they are of the order of 10 to the minus 46 for spin independent, right? In this case,
you want to say something about spin dependence?
okay. So it simply means, so in this case, so the basic idea is, yeah, the basic idea is how your dark matter reacts differently with protons and neutrons. That's how it comes out in the end. In this case, what this means is the vector mediator essentially couples to left-handed and right-handed particles in the same way. The axial vector couples to the right-handed and left-handed particles with a negative sign. So in a sense, in the opposite way. So, so that essentially means that if you have an that essentially results in a different cross section if you have protons or neutrons, and depending on what your target nucleus is, it will give you a different cross section. In the direct detection, you have the nucleus of the target, target material.
Oh,
that's the one that makes a difference.
Not in the interaction, but in the detection.
It's the same thing, no?
Okay.
Yeah, it's
Yeah,
the same
but it's
thing.
in the detection.
Detection that makes a difference, yes. I suspect it has to do with the fact that if you have very light Z primes, then you don't really have a good sensitivity at the LHC because you will be washed out by the standard model dilepton background. So you have Z gamma dilepton background. So to distinguish it, you will need a Z prime that is either massive enough so that the peak is visible over the standard model background, or extremely strong interacting. So it sort of occurs in the cross section, right? The smaller the mass, the higher the cross section, but it gets still buried under the yeah. Yes. I think it's sort of a misnomer. I don't know why it's called spin independent and spin dependent. The way I understand it is the way it couples to up and down work. So does someone with direct detection know this better?
So this axial vector is like S dark matter dot S.
Okay. That's why it's spin dependent. Okay, I see. So it's the low energy effective field theory limit of that is gives you a spin dependent operator. Yeah. Okay. Yeah, there's a gamma phi in this operator, right? That probably gives you that spin coupling.
Yeah, I mean, but chirality is like a high.
Right. Exactly. Yes. Okay. Perfect. Okay, so this is a summary of, so these were Atlas searches. So now we go to the other experiment in CMS, and you can see that they have tried to constrain this Z prime in a whole range of masses, right? So the best limits essentially are in the high mass range. In the low mass range, you can do something, but it's not comparable essentially. So you lose sensitivity either when you go to very high masses because you can't produce them anymore, or at low edge where you produce them, but you have such a large standard model background that you don't get enough sensitivity. So the goal of this plot is to show just that there are a lot of searches and a lot of limits on what the coupling to the quarks can be, okay, in the whole range. So unfortunately, we haven't seen anything, but this is the status of where we are. Okay. So this is just summarizing where we are till now. So we don't want to use EFTs because they have bad high energy behavior. Simplified models get around this problem, and you have much better sensitivity in direct searches. And okay, this was something that we talked about yesterday. And yeah, so the other thing that you should remember is that not every possibility is covered by simplified models. So you can't have a simplified model for absolutely everything. Sometimes there are some more complicated states. So if you are looking at a particular model, then you might be able to escape the limits because it doesn't fall into any of these. Okay, so now the next thing I want to do is to talk about models of getting the dark matter density right that predict different signatures at the LHC. So far we were just talking about missing energy plus something. So there's something more that can happen. So this is the same kind of diagram as before. So remember what happened is in the very simplest case, you have annihilation of just dark matter to standard model. If you have co-annihilation, then you have this dark matter and mediator annihilating together to standard model. So this is together is co-annihilation. You can actually have a case where the coupling is so small that even with this, it is not efficient enough. So what you need to do is you need to kick your dark matter particle into a mediator particle by interacting with the standard model plasma, with the standard model background. So if you do that, then you have the mediator, and then the mediator has very strong interactions with the standard model, so it annihilates efficiently. So there is this two-step process of annihilation. And this happens in particular where this coupling of dark matter, mediator, and standard model is very small, this coupling here. And what this does is it sort of results in this mediator having very small decay widths because the coupling is quite small, right? So if you produce these mediators as before in pairs by reversing this diagram, you have new particles now that are charged under the standard model, but with very small widths, so they are long-lived. Okay, so this is the classic long-lived particle signature. So the diagram looks as before, except this coupling is very small, so you have long-lived particles. Okay. So this was pointed out that this works and has a feasible phase space in about 5 years ago. And around a decade before that, it was also pointed out that there's another way of getting the dark matter density right, which is the idea of freezing, where you don't have a thermal relic from the early universe as before. What happens in the early universe is you just freeze out the mediators to a very small number. And then later over time, in a non-thermal way, you would basically produce dark matter either by this kind of scattering process or by decay of those mediators. Okay, so these are the two possibilities that can happen. And in this case, again, you have this coupling between the mediator dark matter and standard model particles, extremely tiny. So these might go by the name of feebly interactive massing particles, or FIMS. Again, here, the way you look for these is similar because the coupling is very small, the decay width is very small, so they are long-lived. So again, you reverse this diagram, you produce the mediators in pairs, they'll decay to standard model plus some dark matter, but decay much later. Okay. So the smaller the coupling, the larger the lifetime. That's the thing that you should remember. So we can, yeah. Yeah.
The bottom two,
huh.
aren't they effectively the same diagram, that is dark matter mediator?
Yeah, so basically there's also a time component, so it proceeds from here to here. So dark matter annihilating to standard model. This is dark matter and mediator annihilating standard model. This is dark matter and standard model producing a mediator and a standard model particle.
These two.
It's the same diagram.
Same
yes,
diagram,
it's same
so
diagram. It's just yeah.
Yeah. So therefore, both should be equally powerful.
It's not, because this guy is generally slightly massive than this guy. Yeah, yeah. So this thing is actually sort of out of equilibrium because this guy is massive. So you're producing it and then it immediately decays right away. So yeah, this guy doesn't.
The density of
M is low because this process is extremely efficient.
Okay. This is also called, both of these are called deepening.
Yeah, so this one is fairly new. So yeah, you don't. Yeah, so it's either called co-scattering or conversion-driven freeze-out. So you convert it to a mediator, and then that is what freezes out. But yeah, you can still call this feebly interacting because you can. It's now been found that you can actually have these couplings smaller than what this freeze-in requires. So you can have a much larger phase space, actually, a parameter space, I mean. Okay. Okay, so we looked at now two examples of newer ways of getting the dark matter density right, different from the standard freeze out picture. Standard simple picture where you just have jets plus met. Okay. So you can ask, can you see such models in some other search channel? And because these couplings to standard model are now very, very small, it basically kills your signature both in direct detection and indirect detection. So if your dark matter density was set by one of these processes, then you will not be able to detect it in any other way. So your only thing that you can do in this case is to try and produce it at colliders. Okay? So in both these cases, because you have these mediators that are charged under the standard model, you can try to produce them at the LHC. And because they are long-lived, they are likely to give you some slightly more spectacular signatures with low background as compared to your standard jets plus met or leptons plus met kind of signature. Yeah.
What is long-lived in terms of signature?
Yeah. So here, what that would mean is that maybe it will be clear in a okay, let me answer and then it will be clearer in a yeah. So it's produced at the collision point as before, but it doesn't decay right away. So for example, if you have a charged particle that is being produced, then it will leave a charge track similar to an electron or a muon and then decay later on.
Oh, it's completely on shell.
It's on shell. It's always on shell. It's no, yeah. So these, yeah.
That's why you're talking decay time.
Yes, yes, yes. So the process is just this. So these mediators are produced on shell and then they decay afterwards. Yes. Yes. Exactly. Okay. So this is a sort of a classification of what is the initial underlying idea to get the right density. Let me not call it relic density. So if you, depending on what your process is to get the density, that predicts what the signature at the LHC is going to be. So this was the initial idea that we had, freeze out, where you had only the invisible particles. So you had this jets plus met, or you have invisible particles with some extra particle with standard model charges, in which case you can have both also leptons, or you can have gauge bosons. So this is what we talked about yesterday in our examples. Now, because you have very low couplings, you basically predict these long-lived particles, and the signatures are different from before. You can have something like heavy tracks, so heavy charged particles that leave tracks. You can have leptons that are displaced. So this again, we talked about a little bit yesterday, where you have a particle that decays a little bit further off. So the leptons that come out don't trace back to the interaction point. Those are what are called displaced leptons. Instead of leptons, if the particle decays into quarks, then you will have what are called displaced vertices, because you'll have multiple mesons coming out from the same point. You can also have, if your mediators are light enough, you can also look for them in decays of heavy mesons like B quarks or kaons and so on. There's one thing that we didn't talk about so far, which can happen, is that you have an extra whole hidden sector similar to our visible sector. Like the visible sector has protons, neutrons, electrons, lots of things, right? So it might be possible that dark matter sector is not one particle, but actually a bunch of particles. The simplest thing you can think of is a confining theory, SUN, where you have basically dark protons and dark neutrons, right? So that would be something hidden SUN. And in that case, if you produce these, you will have signatures similar to jets, except that everything will be on the dark side. So these are called dark showers, similar to QCD showers in standard model. And in that case, again, depending on how the dark sector communicates with the standard model sector, you can have all of these signatures. Okay, so I'll come to this in the end. The idea is you have dark pions, right? And if you have, say, a Z prime mediator, the dark pion can decay again via this mediator into standard model, right? So depending on what the decay length of this dark pion is, you either have jets that come directly from the interaction point or that emerge a bit later on, because you have these in neutral pions that, so yeah. So you have a fraction of the pions that remain invisible. So they are semi-visible jets, or you have jets that occur later on. So you have emerging jets. Okay. So let's try and understand this language of these long-lived particles a bit better. So I talked a little bit about how this was this was an animation, but we can use this. So you remember, this is the schematic picture of the CMS that we talked about yesterday. So there's a tracker detector inside. There's a calorimeter for electromagnetically charged particles. There's a calorimeter for hadrons, and then there are muon chambers, right? So if you have a charged particle that exits your detector, then basically it looks like this. It has hits in the tracker. It also has hits in the muon chamber. Okay. And if you have, so let's go through this one by one. So the first option is where you have new leptons that are being produced in the decay, but they don't trace back to the interaction point. In that case, you have what are called displaced leptons. So if you have, for example, a displaced muon, you will see that its track goes like this. So it doesn't meet the interaction point. So these are what are called displaced leptons. If you have an invisible particle that decays into quarks, you'll have many mesons that come out. So you basically have the tracker that has some tracks that give you a vertex. So you have a displaced vertex. Okay. Then you have a charged track like this that goes all the way out. So it's a heavy charged track. The thing to remember here is that if a particle is massive, it takes longer to go out. So it will be a slower track than the usual mu1. So the experiments have to basically make sure that they take into account this time of flight. And sometimes if the charged particle decays in the middle, then you have what is called a disappearing track. So these are multiple possibilities of what can happen. So,
Does the muon chamber not capture all the
it doesn't stop them. So they deposit very little energy and they fly out. So you just basically map what the track was like. So we were talking about Mathusla yesterday, right? So their idea is something similar. Like they will not maybe stop everything, but they will just look at the tracks later on. Yeah.
So is it for detection? Is it better if secondary decay happens in the detector or outside the detector?
So there are there's multiple things that that are problematic. So first of all, the way you determine momentum is basically how a particle bends in a magnetic field, right? But it depends also on the mass of the particle. A different particle of different mass will bend in a different way. So your momentum determination will change also if you have a different mass. So this one-to-one correspondence breaks down because you have more parameters now. If your mass is also different, then you have, so you basically your charge and your mass are what are become uncertain. So it's Q by M kind of behavior, right? The higher the charge, the more it bends. The smaller the charge, the less it bends. The smaller the mass, the less it bends. So there are some assumptions that charge is equal to 1, mass is equal to mass of mu1. That is the standard reconstruction technique. So if you want to do something else, then you have to sort of change your algorithms.
No, my question was,
Yeah.
there's an example here where
Yeah.
a particle decayed inside the detector. So what is
Yes.
is it better for detection if the particle decays outside the detector and then you then detect the daughter particles, or is it easier for reconstruction of the decay happens in the detector?
So yeah,
doesn't
again,
matter,
no. So
It
for
will detect
this will have certain advantages in that if you have tracks, then you can reconstruct the mass of the vertex. So in principle, you could find out the mass of the decaying particle. So you could have certain advantages. Sorry, so I was jumping the gun in saying that there might be a way to reconstruct mass better here than with this charge track case because there are more degeneracies there. But yeah, it's not, the reason I'm not giving you a clear answer is because it's not clear to me that this is better, because you might have some invisible particles in the vertex that have flown away and you don't know, right? So you will construct the vertex mass, but whether that's you're capturing everything that came out or only part of what came out is not obvious. I mean, there's no way for you to know because there's no there's no way to attribute missing energy to one vertex or another vertex, or this more complications. Okay, so since we're actually already out of time, I'm not sure how much how much details I should go into, but the idea is that
We have more time.
okay, okay, yes. So basically, you have limits on the cross section for each of these kinds of particles. So the first is these heavy charge track searches. So you can see there is a limit on cross section. So we talked about yesterday how these limits come about, right? So you have this limit from observation, and then on that you can basically superimpose what your theory predicts. So this theory is a simple model where you have a charge track of charge 1, so same charge as electron or muon or tau, and you see that it falls like this, and then you can say that this is the limit on these kinds of models. So CMS has many different predictions for different kinds of particles. What they also do is they try to look for different charge assignments and different spin assignments. So this is spin half, this is spin 0, this is also spin 0, and these are, I believe, spin half as well. So depending on spin, you produce more or less because there's an enhancement because you sum over all final states in your cross section, right? So if you have spin, you have an enhancement. Plus, if you are charged under strongly produced process, strong charge, then you produce a lot more of them, so your limit is much stronger and so on. So you can look at this figure and figure out, depending on your model, what is the exact limit. The next case is the disappearing track, where you still have a track, but it stops in the middle of the tracker because it has decayed, right? So here the limits are in a slightly different parameterization, where they try to rule out for what values of the lifetime of this particle, what masses are ruled out. Okay, so this, as you can imagine, necessarily requires assuming a model. So the model they have is similar to the model that we discussed yesterday, where you have a charged and a neutral partner. Okay, so this is this chi plus and chi zero that we talked about yesterday. It's slightly different, but quite similar. And the thing to take away from this is that there are certain lifetimes which are for which you have the highest sensitivity. If the particle decays too early or too late, then you are not as sensitive in this search. So there are limits from these searches as well. And then you have limits from displaced leptons. And okay, I'll admit you inside. Yes, exactly. We can announce now that we have dark matter detection and you can go home. Let me also get rid of this. No worries. Okay. So all right. So I showed you a lot of models and a lot of plots. So one thing you can ask is that if you so since supersymmetry was such a popular model, a lot of people ask, when will supersymmetry be ruled out? Right? That's a popular question to ask. So this is an exercise we did where we tried to map out. So supersymmetry essentially has 3 parameters for the dark matter sector. So we talked about the singlet triplet model yesterday. You can also add a doublet state. So in SUSY, you have all 3, singlet, doublet, and triplet. And so you can play with the masses of these 3, and you can figure out what combination of them will give you the right dark matter relic density. Everything is freeze out in this case, or maybe co-annihilation. So in that case, you find a surface in this three dimensions that gives you the right relic density, and you can ask what is ruled out by what. The thing to note is that the highest mass that you can reach is about 2.7 TeV. So we haven't got there at the LHC yet, but these regions are more sensitive to indirect detection searches. Whereas you can also have these Higgsinos, which predict a mass of 1.1 TeV, and there was a tantalizing signal last year where you had a charge track search that had an excess exactly at that mass. So it was kind of generated a mini excitement for a while. Okay, so the other thing you can do is that because now you have so many searches and so many limits, you can try to reinterpret them for new models. So whatever model you want, you can interpret that search for your model. So we have a code that is called Checkmate that tries to provide these limits for whatever model you want. So you just provide it with Monte Carlo events, and it tells you whether your model is ruled out or not. So without going into details, the thing I want you to notice is that these different searches can constrain different regions in lifetime and mass. So in this case, you have a simple model where you have a new scalar that goes to a lepton and dark matter. And there are some constraints that you get from displaced lepton searches, some constraints that you get from these charge track searches, but this is by no means constraining everything. So you can have definite gaps in the middle, and then you need new searches, like for example, a track with a kink. So you have a charge track, and then it goes into a lepton, so it looks like it has a kink. So that might be able to fill this gap. So it's important to have all of these on the same plot in a sense, because then you realize that you might be missing some parameter space or subphase space. So let me skip this part. So this is the model that we talked about yesterday, where you have a singlet state and a triplet state, and the mixing essentially results in two neutral guys, and then you can produce the charged particle, which is long-lived because the mixing is small. Okay, so you have different kinds of searches. So we went through these in detail. You can have missing energy plus leptons or jets, and now you can also have tracks from these long-lived particles. So you have an additional handle over this model. So we talked about this yesterday, so let me not go into this. So then this is the second model that we were talking about, which was freeze-in, right? So the last example was now of co-annihilation with small coupling, co-scattering with small coupling. So now you have freeze-in. So again, you have these mediators with small coupling. So again, you can play the game where this mediator is charged under either strong or electroweak, and then you have the same kind of signatures. So you can ask what kind of limits you have on this model. So again, you will see that different lifetimes of this mediator are constrained by different searches. So you have one constraint coming from charged tracks when the lifetime is extremely long. So very small couplings. When couplings are not as strong and the mediators decay in the detector, then you have constraints from these displaced leptons, because you will be able to detect the leptons. And then the middle part is sort of filled with disappearing tracks. So the takeaway from this this plot is that you need to perform all of these searches together to be able to say something about the model. Just having one search is not going to be enough. Okay, so this is mainly what I wanted to convey to you, that there are these new kinds of searches called long-lived searches that will constrain a different class of models than the standard WIMP picture. But that's of course not the end of the story, that you can make models more and more complicated and get more and more signatures. So I just wanted to flash these things. So there is an example of a supersymmetric model where you have extra displaced vertices because this last leg of the decay is sort of long-lived, and then you can come up with searches for that. And the last thing that I want to show you today is what I was telling Arun about earlier, which is what happens if you have this whole dark sector that is hidden. And so there are searches now. So this is the first of the published searches that are trying to look for this as well. So the idea here is that you have some mediator between our standard model and the dark sector, right? So they've just assumed a scalar mediator, and then you produce these dark quarks, and then you have the same kind of dark gluons, and those dark gluons split into dark mesons and blah, 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 the same thing that happens in the standard model. And at the end, some of these dark mesons decay back into standard model particles. And so what you will have is jets that have a component that is invisible and a component that is visible. So this is different from what we talked about before, because earlier always the jets were very well separated from the invisible particles. So you remember the missing energy was not aligned with any of the jets. It was basically a subtraction of everything else, and the missing energy was in a different direction. In this case, you have a weird situation because you will have two jets, but the missing energy is aligned to the jets. So it will be in the direction of one of the jets itself. So this is something that is usually thrown away by the experiments because it looks like you're just mismeasuring the jet energy. They don't want to look at this usually because it seems like this is a wrong, it's a mistake. So the important takeaway from this was that if you have these hidden models, you might have signatures that look like noise or that are considered noise currently. So it is important to look at the theoretical parts of it so that you know that these signatures might exist, and then you have to design specialized searches for this. Yes, so in this case, yeah, so this you could also do this with Suzy, but yeah. The actual model to consider is this, but I guess this is an easier model to simulate. Here? No, it just has to do with the way it decays. So you could, so You could even do a more simple case. No, it doesn't have to do anything with that. So you can just think of something like this, right? Where you produce your dark quarks, you have showers here. So basically what you have in your detector is you have two jets. I call them jets. But these are all dark mesons and dark hadrons. So your detectors will not pick them up, right? Because they don't interact with you. But what will happen is you will have these dark pions that can decay to standard model fermions, right? There'll be a small fraction of these that will decay, right? So, I mean, okay, so suppose you have, so remember in the standard model, you have pi 0 and pi plus, right? Pi plus decays because you have a weak interaction, decays via W. If you don't have a weak interaction, pi plus is stable, right? So if you have a dark pi plus, it will be stable forever. So this will be your dark matter. If you have pi 0, your pi 0 can decay. Either you can have an anomaly like diagram where you have Z prime, Z prime, and Z prime decays into whatever, FFR, FFR. You can have something like this. Or you could also just have, if you have your Z prime is axial vector, then you can just have like decay through that longitudinal component as well. Yes. No, it doesn't. That's what I'm trying to say. So you have some pi pluses and some pi zeros, right? So the pi zeros give you the visible mesons. Let me just call that M. And the pi pluses stay invisible forever. You don't need color. You don't need anything else. It's just your it depends on if these pi zeros are long-lived or not. Pi pluses are always invisible, right? They don't decay anyway. So you always have an invisible fraction. You only have pi zeros which can decay. If pi zeros decay in a short lifetime, then you have just jets with an invisible fraction. If they decay with a long lifetime, then you have displaced jets or emerging jets.
So Nishita, maybe I was prejudiced by the last paper. So do you know in this last jet substructure paper, do they look at like really fat jets or they look at smaller jets?
So there, as far as I don't fully remember what they tried to do. I'll have to look it up. It's been a while since I looked at that paper. So
Collimation is not necessary.
no, it's not. It's not. Yeah. Okay. Yeah. So what I wanted to tell you with this slide is that you can have signatures that are non-standard and not used in your usual picture that you need to see. Okay. So let me skip this. But if you want to look at the current limits on all kinds of long-lived particle searches, there are these summary plots like this. And there are other cases that we did not consider. For example, heavy neutral leptons, where you have like sterile neutrinos, which you can produce via W+, and then you can constrain the mixing between that neutrino and not mixing, but the coupling essentially between that neutrino and a particular lepton. So with electrons or with muons, and you will have limits like this from these searches as well. Okay. So, all right. So I'll end here. So what I wanted to tell you in this talk was mainly that depending on what you assume is your dark matter production mechanism in the early universe, that sort of sets how you would produce them at the LHC. And it sort of may give you unusual signatures if your production mechanism is different from standard. So it's important to look at different lifetime ranges as well as different channels of detection to get an overall picture of what is possible. So you can't just look at some supersymmetric searches and say, oh, there is no dark matter, just because you looked at those 5 searches and you're done. So you might have signatures that you might just be throwing away because it looks weird or it doesn't look like anything standard. Okay, so I'll stop here. Thank you.